And welcome back, everyone. At this point, I'm not sure what part we're on. I think it's part 7, part 8, something like that. Doesn't matter. Let's recall where we left off in terms of the congruent number problem. Right now, we know that a natural number n is congruent if and only if the L function of the associated elliptic curve vanishes at 1, and one direction of that equivalence does rely on the weak Birch and Swinnerton-Dyer conjecture being true, and the other direction is essentially Coates-Wiles. Okay, and what we saw last time is we're going to be able to basically take this information that we've been working with in elliptic curve land as it relates to the congruent number problem and move it over to the land of modular forms. And the reason for that boils down to this I guess you could call it a theorem that we came up with last time. And it says that the L function of a congruent number elliptic curve, which we already knew was the sum from 1 to infinity of this Dirichlet character chi sub n evaluated at m times b sub m to the negative s, where these b sub m's are the coefficients of the L function of E1. These coefficients here actually arise from a cusp form of weight 2 for the congruent subgroup gamma naught of n, which remember is the set of all matrices in SL2Z that have lower left entry 0 when you reduce the entries mod n. And what is this capital N? It's 32 little n squared if little n is odd, and it's 16 little n squared if little n is even. And so these coefficients aren't just nothing. They're not just random or arbitrary. They come from a cusp form. And the other thing that I want to emphasize that I have not done a good job of emphasizing so far is you might ask, it seems like everything sort of relies on these b sub m's. Are these a mystery? Are these unknown? Are these known? One thing I just want to say real quickly is that these b sub m's are easily computable by hand. Okay, so it's not as if we don't know these. And I'm going to talk more about this later, but there is no real missing piece of the puzzle here as a result of us like not knowing all of the BMs or some algorithm for computing them or something like that. You can actually compute them. Okay, so as I wrote here, this is the bridge from the world of elliptic curves to the world of modular forms that we've been needing. And so now we're going to continue on, and I'm going to bring big theta back up again. So remember, what is big theta? Big theta of z is the sum over the integers of q to the n squared, where q is our usual variable e to the 2 pi I z. Okay, and z is in the upper half plane. Okay, so I've been teasing and slowly, bringing up properties of big theta for a little while now, but we're going to continue that trend here. Because what we're actually going to need to continue is the functional equation for big theta. Now, if you go back earlier in the lecture, I think it was even last lecture, we did prove a kind of functional equation for big theta squared, but that's not going to end up being good enough for us, as you'll see later. We're going to want to find a transformation theta formula for big theta itself. So we're going to take a typical square root branch having positive real part, and we're going to let epsilon sub d be the following. It's going to be the square root of the Legendre symbol -1 over d, where d is odd. Okay, so the typical Legendre symbol, take the square root. And it's a standard fact from probably elementary number theory that this is going to be 1 when d is 1 mod 4, and it's going to be I when d is 3 mod 4. Okay, so this is known, you can compute this easily. And then we're going to define this, this thing called the automorphy factor, which you're going to see why it's called that in just a moment, but it's going to be this j of gamma z. And what that's going to be is you're going to take some gamma in big gamma naught of 4, okay? And maybe gamma has, I probably should have written this, but gamma will have entries A, B, C, D. Okay. Then you're going to take the Legendre symbol of C over D. Then you're going to invert epsilon sub d and multiply by that. Okay. And then you're going to finally multiply by radical cz plus d. And z here is going to be in the upper half plane. And then huge incoming theorem. This is very difficult to show, but here's the functional equation for big theta. Big theta of gamma acting on z is the automorphy factor at gamma and z times big theta of z. And it's very interesting with this functional equation, because if you actually go back through the notes and extrapolate just a little bit, you'll discover we actually already proved the square of this, which means this is true up to multiplication by plus or minus 1. Okay, but is it plus or is it minus 1? That's the question. And it's very difficult to show, actually, that it's a plus 1 and not a minus 1. Okay, so I find that strangely compelling, that the square of this is easy to show, but somehow the actual functional equation for this is not easy to show. But there you go. Big theta has a functional equation. And now you can see why this is called an automorphy factor, because when we're defining modular forms, we have this automorphy condition, right? Like f of gamma z equals cz plus d to the k, f of z. This equation sort of looks like that. If you replace f by big theta, if you replace this expression here by j, and this f here by big theta. And if you look at this expression cz plus d to the k and the automorphy condition for a normal modular form, you'll see it's very similar to this expression for j. In the case k was like 1/2, for example, you would get a cz plus d to the 1/2. Now you do have this extra junk out front here, but these are just units, right? This is just like 1, -1, I, -I, things like that. Okay, so it's almost like an automorphy condition for regular modular forms times maybe some unit. Okay, and the reason this theorem is going to be so important for us is that we're going to at some point have to define appropriately modular forms of half integer weight, which we have not done yet. And if this functional equation didn't exist, there would be no natural way to do that. And so more on that soon. Okay, so there you go. Big theta has a functional equation. Now I'm going to promptly stop talking about big theta, like it seems like I always do. I always bring up a property of it and then stop talking about it. So I'm going to do that again. And we're going to go on and we're going to talk about Hecke operators. So everybody who's into operator theory at Toledo is going to have a very fun time with this, I suppose, or maybe not. I don't know. To talk about Hecke operators, we're going to first need to define the notion of a modular point for a subgroup of SL2Z. Now, there are 4 special subgroups of SL2Z for which we want to define modular points, and there's a different definition for every subgroup, but really all you need to focus on is the second one as I bring it up. So I'm going to give you all 4 of them, but really you just need to keep in mind the second one at each stage. Okay, so if the first case is what happens if the subgroup is just SL2Z itself, then we're going to say a modular point for that subgroup is just a lattice, okay, in the upper half plane, a lattice L. If the subgroup is gamma sub 1 of n, so all the matrices that have 1s on the main diagonal and 0 in the lower left corner when you reduce the entries mod capital N, then we're going to say a modular point for the subgroup is not just a lattice, but it's going to be a pair L comma Z, where L is still a lattice and Z is, in the torus C mod L, is a point of exact order capital N. Okay. If the subgroup is actually gamma naught of n, then we're going to say that a modular point for the subgroup is a pair L comma S, where this time L is still a lattice, but now, oh, you know what? This should be a capital S, not a lowercase s. It's not going to be L comma a point. It's going to be L comma a cyclic subgroup of order n in C mod L. And again, I don't know why this dash is here. So in other words, S is just like Z times some T, where T is a point of exact order n. So it's just a little bit of a step up from what we had in case B. And then if my gamma prime is actually a full congruence subgroup, like one of the OG congruent subgroups that we defined, just gamma of n, so the matrices that are the identity when you reduce them mod n, then we're going to say a modular point is a pair still of a lattice and then a tuple of two cosets, Ti, that form a basis for the points of order n. Okay, so don't worry too much about these three. This second one is really what we're going to be focusing on, but I wanted to give you guys the complete kind of picture here for the 4 different special types of subgroups. So we're looking at pairs, lattices, comma, points of exact order n. Okay, so once you've defined modular points for a subgroup, you can go on and you can talk about modular functions on the set of modular points. So we're going to say a complex valued function f on the set of modular points is of weight k if for all complex numbers lambda, going case by case, a through d, as we did up here, f of lambda at L is like lambda to the negative k times f of L. This should look familiar to you. This looks like an automorphy condition for a modular form, and that's no accident, as you'll see in the upcoming theorems. And this needs to hold for every modular point L. And then there's a similar condition for the other 3 cases. Maybe I won't say the other 2 out loud, you can read them for yourself, but for part B, we're going to require that f evaluated at the modular point lambda L lambda t is, you still get a lambda to the negative k out front, and then just times f of lt. So you're really taking like complex scalars, pulling them out of your function, and raising them to the negative k power. That's really what's happening. And then you have something similar for C and D, and this has to hold for all modular points LT. Okay, so as a quick example, if you take the Eisenstein series G sub k, and you view it as a function on lattices instead of as a function of points in the complex plane, there's a natural way to do that. You can view the Eisenstein series as a function of L by just considering it as the sum over all the non-zero lattice points of L to the negative k, which is the same definition we had for the Eisenstein series before, but we weren't focusing on the lattice the points came from, in as much as we were writing those points as like nz, or like nz plus m, and focusing on g as a function of z. Here we're just focusing on it as a function of L. Okay, so you can change the lattice, you'll get a different Eisenstein series, is really what I'm saying. Okay, and then you can actually take this a step further. So you've got modular points, then you've got weight k functions on the sets of modular points. And then you can do one more thing. You can kind of normalize the situation as follows. If I give you a function on the set of modular points for a lattice, and then let's say I take a lattice L sub W, where W is W1, W2, and W1 and W2 actually span the lattice. Then what I can do is I can always make a new lattice. We've talked about this before by kind of rotating and scaling the spanning vectors so that one of them is 1, and then one of them lies in the upper half plane. When we do that, we get a new lattice that sort of has the same fundamental parallelogram, like rotated and shifted, scaled a little bit. We call that L sub Z. And it's going to be the lattice not spanned by W1 and W2, but by Z and 1. Okay. Then you can define, again, case by case, this F tilde guy. And the advantage with F tilde is it's not really a function on lattices or on modular points anymore. It's really just a function on like a single tuple here, it's a lot more compact and easier to understand. And you'll see in proposition 31 what the use of this is, but you're going to define F tilde of W to just be F of L sub W. So F of your lattice. In the case, the congruent subgroup is just SL2Z. And then I'll define what it is for case B, and I'll leave you to read about what it is for case C and D on your own. But F tilde of W, in the case that the subgroup is gamma sub 1 of n, is going to be F evaluated at L sub W, comma, W2 over n. okay, which is a point of order n, exact order n. So you're taking these weight k, well, you're taking these functions on modular points, and you're making them easier to understand by giving them all a single input variable w. And then finally, what you're going to do is you're going to define little f of z to be basically f tilde of z comma 1, which you could also think about in the full congruent subgroup case, or in the full group case, as just like f of lz. Okay, so you're going to define it to be f tilde of z comma 1. And so what's going on here? What does all this mean? It all really boils down to this proposition here. So let k be an integer, and let gamma prime be one of the 4 types of subgroups of SL2Z that we talked about above. Then what you can do is you can find all of the modular points for that subgroup, and you can form this map that sends a function on that set of modular points, capital F, to its tilde. And then you can always send f tilde to lowercase f using this definition down here. So we're going to send f to f tilde to little f. And it turns out this is a bijective correspondence between 3 different sets. The first set on the left here is all the weight k functions on modular points. And we just defined what that meant above. The second guy, the second set corresponds to this middle thing in the map here, this f tilde. And what it is what are these? These are really functions on vectors, right? Like w is a vector. And which vectors? Vector functions on vectors which are invariant under members of the congruent subgroup you're looking at, and that satisfy another weight k looking condition on f tilde. So not only does f satisfy this weight k condition up here, but f tilde also will, which isn't that surprising, right? Because f tilde just comes from f. So, but then you move to the third set. And what is the third set? It's actually just the set of all functions on H that are invariant under bracket gamma for all gamma in gamma prime. And so it then becomes natural, because what does this mean? What does it mean that f is invariant under bracket gamma? It means when you do f bracket gamma sub k, you just get f. And remember, what is this bracket gamma? It's just cz plus d to the negative k times f. Okay, so this is the condition that shows up in all the definitions of modular forms for the full group SL2Z and for all the special congruent subgroups. So really what happens here is this correspondence is bijective with the set of all functions that satisfies the automorphy condition part of the definition of modular forms. We're still not, we're not requiring these F2B modular forms completely, in the sense that I don't see anywhere here where we are requiring that they satisfy meromorphicity at the cusps, but we want them to at least have the automorphy condition part of the modular forms definition. And so what you can do then is you can very naturally define a function on modular points to be a modular function or modular form or cusp form if little f is. Because the only thing stopping little f from being a modular form is the meromorphicity at the cusps condition. We already have the automorphy condition for free. Okay, so that's just a lot of technical jargon. What are we going to do with this? Well, okay, again, really, I want you to just focus on the second case here, where the subgroup is big gamma sub 1 of n. Okay, so we're going to focus without loss of generality on that case. And we're going to define this kind of math cal L symbol. I don't really know how you say that out loud, but I'll just call it L or something, script L maybe. And what it's going to be is the direct sum of these guys that I'm going to write as Q E sub LT. And what does this mean? What we're really doing is we're taking the Q vector, the rational vector space of all formal finite linear combinations of modular points. So these guys right here are just my modular, well, yeah, so these are my modular points. Okay. So I'm taking all finite formal linear combinations of modular points, and it's easy to check that's just a Q vector space. okay? And so you've got a vector space. So it's natural to talk about operators that act on this vector space. And this is where we're going to start to define the so-called Hecke operators. Okay, so here's the first type of Hecke operator. We're going to call it T sub n, and it's going to go from this space L to itself. And it's going, all I really have to do is tell you what it's doing to basis elements. So it's going to send a modular point L comma T or E sub L comma T, whatever you like, to 1 over n times the sum of these E sub L prime of T's. And what are these L primes? They are lattices that contain the starting lattice L, but little l has to be of index n in big L. So that really means there's like n translates of little l inside L prime, okay? And then we're also going to require, of course, that L prime of T actually be a modular point. Otherwise, we're not actually mapping to the space L, right? So, and we're going to just note kind of quickly here that I'm abusing notation a little bit. This T here and this T here are not actually the same thing. The T on the right hand side is, of course, the starting T mod L prime, but there's no need to harp on that. Okay, it's just a slight abuse of notation. So we've got these operators on the space of formal finite Q linear combinations on modular points, which for us in this case just look like pairs L comma T, where L is a lattice in the upper half plane and T is a point of exact order n. Okay, so that's one type of Hecke operator. There's another type. The other type is this T sub n comma n, and it's still an operator on the space L. However, we're only going to really define it when little n and big N are coprime. Okay, and here's what it is. Again, I just need to tell you what it does to individual modular points. It's going to send a modular point E sub L comma T, or L comma T if you like, to 1 over n squared times E sub L over n comma T. Okay, so you're going to divide the lattice by little n. And again, you're going to keep T fixed, and then you're going to multiply the entire thing by 1 over n squared. If you want to know how all this was discovered and come up with, I'll put it in the language that Akaki used. The Hecke was a beast. I don't fully understand how this was all discovered because it's a little bit untenable for me and for a lot of other people. I've read a lot of Stack Exchange threads on this, but you're going to see in the future that these operators hold a lot of power over the various spaces of modular forms and cusp forms. That's really what's going to happen. Okay. In the meantime, you might ask, do they have any, you know, do they commute with each other? Do they have any nice basic properties? And you do, you get a whole bunch of basic properties. So for example, if I take T sub n1 comma n1 and T sub n2 comma n2 and I compose them, they actually not only commute with each other, which is this first and third guy, but they also both equal T sub n1 n2 comma n wait a minute, comma n1 n2. That's a typo, right? So that's nice. So that really describes the commuting relationship amongst operators of the second type. How do operators of the second type interact with operators of the first type? Well, they just completely commute. So T sub n comma n, T sub m is the same as T sub m, T sub n comma n. And then obviously, what's the next question? Well, do operators of the first type commute with each other? The first thing you end up showing is that if little m and little n are co-prime, then the answer is yes. And not only do they commute with each other, but they both equal T sub mn. Okay. And then you can look at the case when the indices are prime, for example, and you'll discover some other properties. For example, if P is a prime dividing capital N, then T sub P to the L, where L is any power, is actually just T sub P L time composed with itself L times. That's the next thing that you have. If P does not divide N as a prime, then you don't get quite as nice of a relationship, but it's still known and it's still pretty nice. You don't get T sub P to the L is T sub P all to the L. You get T sub P to the L is T sub p to the L minus 1 composed with T sub p and then minus this ugly expression, P times T sub p to the L minus 2 times T sub p comma P. If you take all this information and combine it though, specifically, actually, I believe you need all of this. No, you just need C through E. You can actually show that not only do T sub m and T sub n commute with each other when m and n are co-prime, but all of the T sub n commute with each other. And furthermore, not only that, but the T sub n comma n, where little n and big N are co-prime, and then all of the T sub m's, all of them, they form a commutative algebra of operators. And that algebra is generated by the T sub p comma P, where the primes P do not divide N, and then all of the T sub P for any primes P. So these things have all of the nice commuting properties and kind of functional equation looking things, and they generate a nice algebra. And it's just all of the things you want when you're working in operator theory. I mean, everybody who has heard enough talks on Teplitz operators and Hankel operators at UT is aware of this to some degree. Okay, so so the next thing you want to be aware of is that you can not only think of these Hecke operators as operators on the space kind of script L or calibrated L or whatever you want to call that, but you can also think of them in a very obvious way as functions on the space of functions on modular points, those capital F's that I defined earlier. And you can do that in an obvious way. So for example, did I do this backwards? No, I didn't. Okay. So for example, instead of thinking of T sub n comma n as a function on modular points, I can think of it as a function on functions on those modular points. And what do? Where do I send one of those functions? I just send it to 1 over n squared times f evaluated at the image modular point under the original map up here. Okay. And I can do something similar for T sub n. I can send a function on a modular point to 1 over n times the sum over the lattices containing L with index n of f evaluated at one of those modular points. Notice this expression is just basically the same thing that showed up here. It's just that we're now taking f of this modular point instead of just writing down the modular point itself. Okay. And so here's some nice facts about Hecke operators. So, okay, so let's suppose I have a function on the space of modular points. And let me consider this correspondence up here, where I basically am sending that function to little f. Okay, so here's the first idea. Let's suppose that little f is a modular form for gamma sub 1 of n. Okay, then it turns out if I act on this f with T sub n comma n or with T sub n, then I'm also going to get a modular form in the same exact space. So when it's kind of like, it's like Hecke operators preserve modular forms. If you had to boil this down to just a simple statement. In fact, I think I wrote that here. So T sub n comma n and T sub n are actually linear maps on the space of modular forms for gamma 1 of n. And you can also check they preserve the space of cusp forms. And there should be a period here. And you can also check this holds for the other nice special subgroups of SL2Z. In particular, it holds for SL2Z itself and then also gamma naught of n. So as esoteric and abstract as Hecke operators initially seem, we are already seeing that they play very nicely both with each other and with spaces of modular forms and cusp forms for basically all the subgroups we care about in SL2Z. Okay. So they're actually linear maps, or they can be viewed as linear maps on the space of modular forms under the correspondence above. The next question is like, okay, well, I know that the modular forms for gamma 1 of n can be decomposed, if you recall, into the direct sum over all Dirichlet characters mod capital N of modular forms at level n for each Dirichlet character. We've seen this already. So you might ask, okay, let me zoom in on this space and just focus on one component here. Let me take a modular form that lives here for some character chi, and let me write down its Q expansion. Okay, then I know from proposition 33 that if I act on F with one of these Hecke operators, I'm going to get another modular form in the same space. The question is, are Hecke operators, do they play strongly enough with the spaces of modular forms that we actually can understand what these coefficients B sub n are in, of the Q expansion of the image of F under this Hecke operator in terms of the original coefficients A sub n? And the answer remarkably is yes. It turns out B sub n is just the sum over all, excuse me, of chi of D times D to the K minus 1. Okay, that's all well understood. Times A sub mn over D squared. And if D squared doesn't divide mn, then we'll set this to 0. We'll set the term to 0. So really, we're only considering terms where D squared actually divides mn. And this sum is over all D dividing the pairs mn. Okay. And so if you just boil it down, what am I saying? I'm saying that not only do Hecke operators preserve spaces of modular forms and cusp forms for all the subgroups we care about, but we actually understand what they do to the coefficients of these modular forms. So they're very tightly connected with these spaces. Okay. Now, there's even more structure that these eigenforms have that's going to be that these Hecke operators have that's going to be important to us later. We can talk about the notion of an eigenform for a Hecke operator. An eigenform is just an eigenvector for the operator, basically. So we would say an eigenform for all Tm is an eigenvector F. Maybe it's a modular form, or maybe it's just one of these F's up here under this correspondence. So it's at least something that satisfies a type of automorphy condition. Where am I? Where did I just go? Oh, right here. So, so an eigenform is a function F that acts like an eigenvector for all of the operators at once. So in other words, if I apply T sub m to F, I'm just going to get lambda sub m times F, where lambda sub m are my eigenvalues, one for each m. Okay, and they're going to be, units in the complex, or they're going to be invertible in the complex plane. So they're going to be non-zero complex scalars. And once how do you know any of these ever exist? That's the first question. Like, are there ever eigenvectors? Like, are there even eigenvectors for a single Tm, let alone for all of the Tm at once? The answer is not only yes, but there's some deep structure there, and that's in the form of proposition 40 here. So let's take one of these spaces of modular forms for one of my Dirichlet characters mod n from the direct sum up here. Zoom in on it. And let's suppose that I do happen to have an element F in there that is an eigenform for all of my T sub m. And let lambda m be all the eigenvalues. Okay. Take a look at the Q expansion of F. Write it out. And let the coefficients be the A sub m. Okay. Then it turns out that A sub m is just the eigenvalue lambda sub m times A1 for all m. And unless K is both 0 and F is constant, you can guarantee A sub 1 is non-zero. And not only that, but if you happen to have a modular form that's not a cusp form, so meaning the 0 index term of the Q expansion doesn't vanish, then there's like a formula for all of these eigenvalues. Like, none of this needs to be true at all. This is very rich structure here. So what's happening is the Hecke operators are providing key insights into the structure of certain spaces of modular forms. And by certain spaces, I mean all of the spaces we care about. the individual components of gamma 1 of n, for example. How? It's like they're the operators such that when you apply them to functions, you're ending up with modular, I'm sorry, not when you apply Hecke operators to them, but when you consider them as eigenforms for the Hecke operators, you produce these very special functions, little f, whose coefficients really only depend on the first coefficient, a sub 1. It's like you're able to get all these coefficients here by just twisting a sub 1 by the eigenvalues, which wouldn't even be that interesting, right? Except for that we have a formula for the eigenvalues, which is just crazy to me. It's very hard for me, admittedly, to see why all this structure should be true from the definition. This must have required some kind of incredible foresight on the part of Hecke or other people working with him. I don't understand how they were able to see that how all of this structure was going to unfold like this, but I digress. So, okay, so we still don't actually know eigenforms exist for all TM though, right? I mean, we don't even know eigenforms exist for a single TM necessarily, but we'll talk about that soon. In fact, we'll talk about it down here. The first thing that I want you to be aware of before we do that though is you're often going to see that eigenforms are normalized. Okay, and what I mean by that is you want the first coefficient to be 1. We already talked about this when we talked about modular forms. We talked about normalizing modular forms in general, so it should be no surprise to you that we want to normalize eigenforms a lot of the time. Okay, so here's a really crucial proposition about eigenforms. So first of all, they exist because any weight k eigenform for all TM at once for the full group SL2Z, which is not a cusp form, is the normalized Eisenstein series E sub k up to a constant multiple. And conversely, every single normalized Eisenstein series is an eigenform for all T sub m. So not only do eigenforms exist for all T sub m, but we can completely characterize them as constant multiples of the normalized Eisenstein series E sub k, where one direction is requiring that you're not a cusp form, but that's not a big deal. The point is they exist and we understand them very well. Okay, so these guys, if you remember, what did I write about the normalized Eisenstein series before? Let me just go back up really quick. They were very powerfully contributing to the structure of certain spaces of modular forms before. Let's see, right here. We knew they already generated the entire space of modular forms for the full group SL2Z if K was 4, 6, 8, 10, or 14. And we knew they played a huge role even if K wasn't one of those values. They basically generated everything except for the space of cusp forms. But what I'm telling you now is not only do they do that, but they are actually eigenforms for all of the Hecke operators T sub m at once. So they're playing a crucial structural role, all right? So now back to where we were. So let me give you another example of normalized eigenforms. Oh, shoot, I should not have scrolled all the way back down. Remember the discriminant? Remember how you can view the discriminant of a curve as a modular form if you view it as a function of z? What did I write up here? I wrote something right here. What generates the space of weight 12 cusp forms for SL2Z? The discriminant. And it plays a large part in the structure of the weight k cusp forms for SL2Z for all k bigger than 15. Okay, so you might ask, does it play an important role as far as Hecke operators are concerned? And the answer is yes, and I'm going to tell you a celebrated result that we're not really going to use, but it's huge. It turns out the normalized version of the discriminant, which you might recall is just 2 pi to the negative 12 times the discriminant, is a normalized eigenform for all TM for weight 12 cusp forms of gamma, which is crazy. And here's the celebrated result. You might also recall, I did tell you this, that the Q expansion, or not the Q expansion, but well, okay, so I guess I should have written here Q to the n first. So the Q expansion for this normalized modular form was the so-called Ramanujan sum. So the coefficients are special. They're called Ramanujan coefficients tau sub n. It was incumbent upon number theorists to try to understand these things, or at least get bounds on them, because this guy is such a crucial modular form. And it was very hard to do for the longest time. But what you can do is you can take the Dirichlet series version of this Q expansion and form it. So just replace the Q to the n's by n to the negative s and make a Dirichlet series. It's now possible you can actually show that this guy has an Euler product form, which I've written here. And because of this Euler product form, you can actually get a bound on all of these coefficients in terms of just n. And it turns out the absolute value of tau of n is just bounded by sigma naught of n times n to the 11 halves. And remember, what is this sigma naught? It's just the sum of the, it's just, remember sigma sub d in general was the sum, sigma sub d of n, excuse me, was the sum over the divisors. I'm sorry, I'll use the letter K. I don't really want to use the letter D. It's the sum over all the divisors of n of the divisors to the K power. So what is sigma naught doing? It's just basically counting the number of divisors of n, right? So you're just taking all the divisors to the 0 power. So that's huge. This is a very celebrated result. It allows us to more or less get a very nice bound on the coefficients of the normalized discriminant modular form, which was just something people were not able to do for a long time. Okay, I didn't just bring this up because it's a celebrated result, though. I also brought it up for another reason. If you look at this Euler product, it should remind you of something. If you go back in the notes, I'm not going to scroll all the way up, but go back and check out what the Euler product formula for the L function of the congruent number elliptic curves looks like. You'll see it looks a whole lot like this. These powers are basically different, and this tau sub p is just a constant that depends on n. Other than that, it looks identical to this. And so again, I'm able to show you another example of something that I've been talking about since week 1, which is the connections between modular forms and elliptic curves do indeed run deep. There's a whole lot of things going on here that are very strange. Okay, so there you go. Hecke operators, they somehow get in there into these spaces of modular forms, and they provide even extra structure that we somehow just weren't even aware of. And I don't understand how this was discovered fully. Maybe we can talk about that when I take questions. But the next thing we're going to go on and talk about is the so-called Peterson inner product. Okay. And the Peterson inner product stems from a crucial observation, which is this. Let's say I take the upper half plane and I have some region there, and I have an integral on that region. Okay. Let's say then I make a change of variables on that region. Let's say I send Z to alphas acting on Z, and alpha is just in this huge group of matrices GL2 plus Q, which is the biggest group of matrices we've been working on so far. Then it turns out, and this is not even hard to show, but if dx dy over y squared ends up in your integrand, then the value of the integral is unchanged by this change of variables. Which is, I mean, as far as we're concerned, that's huge news, because we like when we act on complex numbers in the upper half plane by matrices and things don't change. That's what the whole study of modular forms is about, right? And so when people discovered this, and you can check this as an exercise, that led to the following additional discovery, which is this. So let's say I take a congruent subgroup of SL2Z, and I let F prime be a fundamental domain for that congruent subgroup. Remember, what is a fundamental domain? It's a closed region in the upper half plane such that no 2 points in the interior are gamma prime equivalent. And every point in the upper half plane is gamma prime equivalent to some point inside that fundamental domain. Okay. What you can do is you can define the mu of this congruent subgroup to be, you're just going to abuse this fact up here. You're just going to integrate over the fundamental domain of this guy here, dx dy over y squared, that leaves integrals unchanged under this change of variables. And it turns out this integral always converges. And not only that, but it's independent of the choice of fundamental domain, because every congruent subgroup has many, many fundamental domains, I mean, in principle, right? So you might think that this integral should somehow have a different value, you know, depending on which fundamental domain that I've chosen. Although if you've been listening carefully, you'll see that's not the case. But this integral is independent. It always converges. It's independent of choice of fundamental domain. And then you get a nice little fact here that I'm not going to spend a lot of time on, but it's going to come up in the definition of Peterson inner product, so I'm not going to totally ignore it. Actually, if you take gamma and you mod out by plus or minus the identity matrix, giving you gamma bar, and you do the same for the subgroup gamma prime, and you look at the index, it's actually just the quotient of the two integral values. So the index of the subgroup is just the quotient of the two integral values, okay? Mu of the subgroup divided by mu of gamma. And if alpha is any matrix in GL2 plus with rational entries, such that alpha inverse gamma prime alpha, not only is gamma prime in SL2Z, but this this alpha inverse gamma prime alpha also is in SL2Z, then this index here is independent of conjugation. You can conjugate it by any such alpha, retake the index, and you'll get the same index that you started with. And so when people discovered all this, they were like, wait a minute, I think we can maybe make an inner product out of this. So they did. They defined what's called the Peterson inner product for a congruent subgroup gamma prime in SL2Z. And here's what it is. The inner product of F and G will be defined by 1 over this index, which is like independent of conjugacy, okay, times this integral, where I'm not going to integrate the function 1 anymore. I'm going to integrate the function fg bar times y to the k. Okay, where f and what is k? It's the weight of f and g. F and g live in the space m sub k for gamma prime. Okay, and because of all the properties above, you can easily check this is linear in f and antilinear in g. You can check that f inner product with itself is 0 if f is non-zero. And so it's a Hermitian inner product. I mean, it's actually an inner product, which is pretty wild. I mean, we're starting to get into like the realm of functional analysis here now. And then you just have to check, is this integral well behaved? And it turns out it is. The integral converges absolutely. And it's also independent of the choice of fundamental domain. That's this proposition 45 here. And as a matter of fact, you start to get other things from this inner product that are reminiscent of properties of general inner products that you might expect from functional analysis. For example, let's say I have two functions f and g, modular forms for gamma prime. And all I'm going to assume is that this space of modular forms has at least one cusp form. Then if alpha is any matrix in GL2 plus, not even in SL2Z, just any matrix in GL2 plus, then the inner product of F with G is the same thing as the inner product of F bracket gamma with G bracket gamma. And that's pretty crazy. The next thing I want you to be aware of, and I know I'm kind of skimming over this and it seems like it might be hard to show. It's not hard to show. Any space of modular forms for any congruent subgroup is finite dimensional, no matter what the weight is and no matter what the congruent subgroup is. If you take all of the properties of the Peterson inner product and this fact right here, and you combine everything I've said basically today, you answer a fundamental question, which is this proposition 51 here. every single space of cusp forms for any Dirichlet character mod capital N has a finite basis of eigenforms for all Tn. Boom. In fact, for all Tn such that little n and big N are coprime, but whatever. This answers the question I was asking earlier, which is like, how often do these spaces, do these eigenforms actually exist? How often do they exist? For which spaces do they exist? Well, here you go. Here's like a great answer to that question. There is always a finite basis of eigenforms for all T sub n, for cusp forms of weight k, for any character chi. Okay? So when we rely on powerful facts about eigenforms, we can be sure they actually are there, and that they are somehow building up our spaces of weight k cusp forms for characters, and hence often for weight k cusp forms of like gamma 1 of n, if you use the direct sum decomposition, for example. And I'm gonna get through these bullet points today. We're gonna get through section 13 here, but this concept of old form and new form, I debated whether or not to include this, but you may take interest in some of this after I get done with my talks and want to go study a little bit more about modular forms. And I just want to warn you now, you're going to see the words old form and new form a lot in the literature. And it is going to come up, the word new form is going to come up one more time in this talk later. But here's what an old form and here's what a new form is. It's simple. Okay, so let's say I take a capital N and I break it down into two factors, D1 and D2. And let's say I have a modular form for gamma sub 1 of just D1. So it's a level D1 modular form of weight K. Then you know that as soon as you're a modular form of level D1, then you're a modular form of level any multiple of D1, right? So in particular, F also has to be a modular form of level capital N. Okay. We also had a proposition that I believe I brought up last time, that if you scale the input variable Z by, let's say, D2, then F will end up also here as a weight K modular form for gamma 1 of N. Okay. So it's like you can take a modular form for this factored number D1, and you can produce a modular form at level capital N in two different ways. One, by doing nothing, and one, by scaling the input variable by the other number, D2. The subspace of cusp forms of gamma 1 of N spanned by the forms gotten in one of these two ways is called the space of old forms. So that's a bit mouthy, but I can describe it if you want a catchphrase to remember for what old forms really means. Old forms are cusp forms that are actually cusp forms at lower levels than the level you're considering. Okay, that's really, if you want to just have one sentence in your mind, they're cusp forms that actually come from a lower level than the level you're working at in one of these two ways. It turns out Hecke operators actually preserve the space of old forms, of course, because what do Hecke operators not do? I mean, they do anything you want, it seems like. And so then what's a new form? Well, okay, so you can take the space of old forms and you can consider its orthogonal complement with respect to the inner product. And what you get is the space of new forms. And again, if you want a simple way to think about new forms, you just want to think of them as like modular forms or cusp forms that don't come from a lower level like these guys did. Okay. So more precisely, F is a new form for S sub K of gamma 1 of N, if and only if, well, Fg is 0 for all G in the space of cusp forms at that lower level D1, and this inner product expression here is 0. So I'm not going to say this out loud, but there's an inner product, there's an orthogonal complement condition that has to be satisfied. Okay. And another reason I'm bringing up old forms and new forms is this concluding statement here. Not only does S sub K of N chi have a finite basis of eigenforms for all Hecke operators T sub n, T sub little n, where little n and capital N are coprime, but that same fact holds true for the space of Newforms, and you no longer require the condition that little n and capital N are 1. So every space of Newforms has a finite basis of eigenforms for all Hecke operators T sub n. Bang. That's crazy. That's huge. Because I'll just give you a slight preview of coming attractions. Remember what I said at the very beginning? The very beginning of the talk. We found, well, actually last time, but I just rehashed it, right? Our L functions came from a weight to cusp form, right? That's going to end up being a Newform, okay? So we're going to get to use some of the structure of Hecke operators to talk about this problem and come up with some really powerful theorems that are going to lend themselves to the congruent number problem, okay? So I think that's, what did we get through? Another 5 pages or so? Yeah, perfect. We'll stop there. Next time, we're going to finally define modular forms of half-integer weight. That's going to be another very fast kind of knowledge-based section. Then we're going to talk just briefly about Eisenstein series for those spaces, and then very briefly about Hecke operators for modular forms of half-integer weight. We're going to take all this knowledge we've gathered about all the different types of modular forms, and we're going to hit the congruent number theorem very hard with all of it. Section 17. All right, so I'm going to stop recording now, and if you have any questions, as usual, type them out or unmute yourself, and thank you all for coming.